last week's lecture, and this one is kind of interesting because we had a lecture on recursion. And on the recursion lecture, I emphasized that the secret of understanding recursion is to understand that there is no secret, that nothing happens in a recursive function call that wouldn't be happening on any other function call. So when you have a problem that you break into smaller pieces, that normally those pieces are different from your original problem, and then you use some different function to solve them. Hopefully that function is in the standard library, as it often is, that you don't need to reinvent that wheel. But if your problem is self-similar, that it consists of smaller pieces that are the same type as the original problem, so recursion is just breaking a problem into smaller pieces, and then instead of calling some other function to solve a smaller piece needed to solve the entire whole, just call the same function again. So the recursion, many people find it that it's something like a hinky and strange, but that's just because we're confusing three different time periods: the time when you're typing in the code, and the time when you're running it. The Python is reading it and compiling it. Yes, Virginia, Python is a compiled language in every sense of the term. It's just that you don't need to explicitly initiate the compilation yourself. And then there is the runtime, and these three times are completely separate. So it seems kind of like a cheating for some, and I can understand it would be like a normal. It goes against our normal intuition that the function can call itself even though it's not yet done. So, but it's not done while you're typing it in, but once the program is running, so then the recursive function is existing in the same sense as all the other functions that existing in Python, and calling it so making a recursive function call, absolutely nothing happens that wouldn't be happening in any function call anyway. So that this we now the same principle here. We saw the generator. So generator, we wrote the programs functions that because we use the keyword yield, so then they produce the values one at a time, and in they always remember where they left off. So ordinary function, when you call it, so it creates a fresh new namespace, but then the namespace ceases to exist once the function returns the answer. Whereas a generator object, so it maintains its internal state of computation, the namespace of its local variables, and the state where the execution is currently at, and then at every call continues where it previously left off, so after the yield statement. So now when we wrote the example generators, we wrote the generator decorators, we realized that the generator being a function for all relevant purposes for the execution of its statements, so you can call another function, so that function could be some recursive function, but that's not the weirdness. But so we realized that the generator often is defined based on an existing generator, typically range, but could be any other. And now, so again, so if a generator is defined by using a simpler version of the same type generator, so we make a recursive generator, that there is absolutely no difference in that to writing a generator that uses some existing sequence like a range or similar. So if anybody remembers these memes, I don't know if they're still relevant, but for my fellow kids, so the Joker meme with the Heath Ledger that they do something and suddenly everyone loses their mind. So like make a generator, use another instance of the same generator type, and then suddenly that's somehow like weird. But so then this Morse code encoding, well, encoding is simple because it's just a local operation based on the individual letters, but the decoding, so let's begin a little. So here's an example run that of course made just to make sure that everything is working. But so the recursive decoding, so we see that it's a generator, there's a yield in there, and then as a part of decoding a message, we are looping through all the possible ways to decode the rest of the message once we have extracted all the possible ways to extract the first first character. But now getting a bit ahead of myself. So Morse code. So people of course have heard of this at least, even if, and everybody should know what is DDD da 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 DDD if you hear it. So SOS. So sending you an SOS. So then the Morse code. So as created by Samuel Morse. So now Samuel Morse in the 19th century, of course, we cannot fault him for not knowing everything that was learned in the coding theory and combinatorics in the 20th century. But so Morse code, so every character that is recognized, so here for simplicity I just recognized the Western 26, so then each one is encoded to dots and dashes. So here we have first a dictionary one way, so mapping all this recognized like a dot and dash, so then that means an A, and a single dot is just an E. So well, Samuel Morse of course clearly so I had a practical idea that so realizing that the natural language is not uniformly distributed, that some letters are just more common. So letter E, the most common language in most common letter in the English text, so that one deserves to have a single dot, and then like a Scrabble letters like a J, so it's a dot dash dash dash, and what is the longest, so 4 or 5. So this like rare characters, they get a longer encoding. Now these days, so what is known about this kind of a coding, so this kind of a code instead of dot and dash, so if you think of true, false, 0, 1, so then could be made now what is called the prefix code. Well, maybe prefix-free code would be more accurate, but like the problem here, like we realize that if you see dot dot dot, so then unless there is some kind of artificial space that the operator leaves between the dots, so now in principle we cannot tell. So dot 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 can be either 3 E's or it can be a single S. So we can decode. So let's turn this into a list, because again this is gonna be a lazy sequence. So let's decode dot 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 and see what happens. So as you can see that there is so because I is a dot dot and E is a dot, so this could be E, I, E, or S. So this decode Morse as a lazy generator is gonna produce every possible way to decode. But then of course we're gonna combine this with the word list, so that we only care about the decodings that are actual words, because otherwise so in general the number of ways to decode is exponentially large. So then like just looking at how many ways there's a decode to decode n dots, so then just adding one dot so makes a big combinatorial thing. I'm pretty sure Fibonacci in this example, Fibonacci numbers, they must be there hiding in some form. But back to the dictionary. So we have a dictionary here mapping from encodings to the original characters. So here is the encodings. So then we can quickly take a dot dash and determine whether it's some kind of a single character. Otherwise we have to break it down into smaller pieces. So, but again, so this these days would be done with the so-called Huffman code. So Huffman algorithm, famous one. So basically, in any gonna be somewhere in the second or third year course, one of them. That for if we were given the letter frequencies of these 26 characters, so then Huffman code would be the optimal prefix code. So actually prefix-free code, that we wouldn't have this problem that we have like a one code word that is a prefix of another one. So then prefix code have a nice property that the decoding is unambiguous. So there is also unambiguous codes that are not prefix codes, but the prefix codes by their nature, they are always unambiguous to decode. So using a prefix code, you take a message and encode it, and then you decode it, so it becomes only that original message and nothing else. But now the other way around. So first we have a handy programming trick here. So for the fans of the list comprehensions, so already saw that if you put the square brackets, you get the eager list, and if you put the ordinary parentheses in the list comprehension, you get the lazy list comprehension. Handy to, especially if the underlying sequence also itself is lazy. So then if the sequence is very long, so laziness is good. But dictionary and set comprehension, so both use the same curly braces syntax, but the type of the entry expression. So this is exactly like a list comprehension, but creates a dictionary, and therefore this expression has to be a dictionary entry. So the key and colon the value. So if this wasn't this kind of expression, so then you're making a set comprehension. So you get the set of the elements. So sets are heterogeneous, so can contain anything. But so this one-liner, this must be from some Python cookbook or some similar site that I saw. I thought, like, I forgot where I saw this. But so the idea, of course, like so if you had a phone book, so easy way to, from a given name, to find a number in the old-time printed phone book. So construct a reverse phone book that from phone numbers to name. So the reverse dictionary, so simply by well, first of all, so what happens when you loop through a dictionary? So the loop goes through the keys. So then there is a function that you can loop through the key value pairs, but we don't need, because if when we're looping through the original keys, and then in the reverse dictionary construction, so then it's just the original dictionary value for that key then is mapped to the key. So then this is the handy one-liner to create the reverse dictionary. So if the original dictionary, so all the keys so all the values were unique, so then this creates a dictionary where all the keys are of the same. Like if everybody's got a unique phone number and a unique name, so then the reverse dictionary from phone numbers to names is the same one as the original. Okay, but then the encode and decode. So encode I wrote here as a string function. I don't know what this could. I could just leave out the sep join. So this sep join. So just to remind everybody what it is. So the canonical way to convert a list of strings into a single string. So kind of an upside down way that it is that so you think that the operation of turning a sequence into a string would be operation for sequences, but it is not. But it's much better. It's a string operation. So it's you take a string that you want as a separator. So often it's a comma and a space, so that we get a nice. But so that this separator can be anything you want. So it just becomes, so that is the canonical way to convert a sequence of strings into one string. And then the opposite was the split, that you give it as an argument the separator string. So I think this normal Python string split, you just give one separator, but then in the regular expression module, there is a function for splitting where this one can be an arbitrary regular expression. So then you can have different kinds of separators. But so this join and split, so those are each other's inverses. Okay, so now encoding a message to Morse. So what is encode? So without any breaks or pauses or anything, although where now where keyword arguments rule again. So if we want to find out, so we can give a specifier separator. So age, so is 4 dots. Okay, so there is a character. So so we learned that E is 1 dot, I was 2 dots, S was 3, and H was 4. So that's just with the dots, not just somebody should make a unary Morse code that only uses dots. So E is a single dot. So as you can see, the encoding is straightforward, because so it's just every character. So here taken from the reverse dictionary, because I intentionally made the original. It was the other way around, so that I can demonstrate this wonderful one-liner. So because there is so this can be done with the list comprehension for the reason that the processing of every character is done separately and individually, regardless of its surrounding characters. So normally, when the processing required the window of a surroundings, not just the element and the position. So then we couldn't use the list comprehension, at least without the aid of more convenient iter tools. But here, so whenever the processing of a sequence element is just for that element regardless of the surroundings, so just consult the reverse dictionary and use empty as a default, that for example the space that we didn't recognize or any special characters. That yeah, so well, the separators just we still got the separators here. That I should fix that, but yeah, as well. And then the canonical trick, if you wanna lose the distinction between uppercase and lowercase in your program's functions behavior, so just convert to the canonical representation. In this case, the lowercase letters just look better than uppercase. I don't know why that is, but everyone knows that they do. They're more readable just for the human eye. So just so that part would be the lazy sequence, and we use a sep join to turn it into a string. But let's see an example of this. So let's leave out the spaces so that that's not the point. So we get this one, and then we'll try let's say the previous answer. So remember, in Python IDE, the underscore is like a MATLAB ans, the previous answer. So that one decodes into, it decodes into so many things that I should actually stop that. Let's try something simpler, just a hello. Ways can you break that one down into like an exponential? So then now the encoding, the decoding of a code with the help of recursive generators. So decode Morse, so it's a generator because I put a yield in there. So that fact and that fact alone is sufficient that this one will spit out all the possible decodings one by one in a lazy fashion. And whenever your combinatorial sequence is exponentially long potentially, so now it is extremely important that this is a lazy sequence, that well, even if it's a humongously long sequence, that we're not gonna run out of memory processing it. So maybe it's gonna be some overnight run, or but that's just the deal with the exponentials, so they quickly become so long computations that we cannot do them. But so the lazy sequence galore in here. So what is the recursive problem given the ciphertext? So that's the Morse code now. So decode it back to the English characters, and then in the demo for printing purposes. So when we have so we're gonna be encoding the text. Well, why don't I run the example rather than just blab about it? So a whole bunch of randomly chosen words from the words sorted word list. So zoning encodes to that way and broken down. So then, well, it only produces zoning. But let's see if there is a, well, here is a one that starts with D and N and T. So dash dot dot dash 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 dot dash dash. So that one can, so then we're gonna print out the spaces, so then we can see. So like the problem recursively, so the key to every recursion was bodying the self-similarity. So in the original problem, so how is there a smaller problem of the same type hiding? So to decode a message, so we use a for loop to loop through all the possible prefixes, so all the prefixes here that we recognize. And if the message starts with the prefix, so for example, this message here, dash dot dot dash dash, so it starts with the dash dot dot, that is the letter E. So the head is gonna be the first character that we extract. And once we extract some initial prefix, some non-empty prefix, so we're left with the smaller subproblem so combine the letter D, that we chose to dash dot dot, combine that with every possible decoding of the rest of the message, and do this for every prefix. So we first for the head is gonna be D, and then this tail decodes to oat and ow, so producing dot and dow. And then, so this for loop, once it has gone through all the possible ways to complete this dash 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 dot dash dash, then it goes on to the next prefix. That so just reading through these characters one at a time. We could also do it by reading characters from here in the lengthening until we find no more. So, but this one slightly less efficient, but so slightly that it doesn't matter in here. But just made for a lot prettier code and allowed me to eliminate one of those for I in range length blah blah that I've sworn to. So I'm a self-imposed kill on site order whenever I see those. So then I take the slightly inefficiency in the service of style. So looping through the prefixes, and whenever we find the prefix that the current message starts with, so extract the first character, the head. So ask the code's dictionary what is the corresponding the character. And if I wanted to make this one line shorter, so then I could put this one here and eliminate this one altogether. But in general, so it's just better in this kind of a situation as the programming saying that you ask once and after that you remember. So if it's not gonna change, so this head character is not gonna change in the inner loop. And now the inner loop, so I noticed that this is now a recursive generator because we have a recursively smaller subproblem. So the problem of decoding all the possible ways, so listing all the possible ways to decode the rest of the message. So the message starting from once the prefix has been extracted, so starting from that character. So this tail, if there could be an exponential number of possible ways to decode a long message, and this one by one produce system, and then for each one, so when it's turned one by one yielding. So this whole thing is a lazy sequence that is not gonna be running out of memory, creating some from a planet-sized list of exponentially many combinations. So this is gonna keep producing one by one, and then we could, for example, ask, well, give me the first 10 just to, or we could feed this to the reservoir sampling of some kind of slice and see what happens. But the pretty similar structure of the so extract the first character in all possible ways, and for each first character, so generate every possible decoding for the rest of the message, and then just yield those one at a time. So now we have this arbitrary decoder as a lazy sequence, and then here we're using building an eager list, so all the possible decodings of the message, but only if that word is an actual recognized word from a words sorted word list. So now here also for just we only look at the words that are shorter than 7 characters. Otherwise, we get another expo. Just this random. These could produce such a long encodings that they might have an exponential number of they do, but we wanna keep the exponential small. So now running this again. So let's see what we're gonna be getting. Come on, spider. There we go. This may have been some really long. Yeah, of course, whenever there is a lots of dots in a row, so you're just gonna get some Fibonacci, could be Fibonacci or Quattro, whatever they call it. The Quattronacci numbers might be involved in there because there's 4 possible things to choose from. Hope I didn't just sound silly there. Now here we have a nice short one. So dash da di da di di da. Okay, like in a song. So now this can split into. There can be a C in the beginning. So dash dot, and then the task dot dash. So the thread decodes into a whole bunch of different things. Notice also in the recursion, so not because we're looping, so intentionally looping through the dictionary. This is interesting that I learned recently. Python dictionaries and sets, because of the way the hash table works, so then it's not necessarily the same for you and me. So nothing was guaranteed about the iteration order. But because this so dictionary comprehension and this dictionary, this creates these entries into insertion order and is now guaranteed, Python 3 point something started to guarantee that when you loop through a set or a dictionary, that you'll get the elements into insertion order. So now that this has been built in the alphabetical order, so then this for loop through the dictionary keys is guaranteed to go through the prefixes of the characters in the alphabetical order. So notice often with these kind of recursive constructions that you don't need to sort afterwards. So I've seen students do that many times, but just by organizing your recursion, so in what is called the radix tree fashion, you can guarantee that your solutions are coming in a lexicographic order. So the same, like for example, in the sum of distinct cubes created problem. So just by going through the possibilities, starting from the highest number whose cube fits in and then looking downwards, so guarantees that you by construction you get the solution that is the lexicographically highest. So here we're starting from lexicographically lowest, but that doesn't change anything. So but it just by construction guarantees that you get the solutions in sorted order, and we know already sortedness is power. That's why we keep things sorted, and that's why along a street the buildings are not randomly numbered, but in sorted order. So sortedness, when we get it for free by construction, so always take it. So if somebody doesn't like it, so they can go jump in a lake or they eat a lemon. So they can always shuffle, and when shuffling, so use the node shuffle. And then maybe if they use some silly shuffle, that's their problem. But now the recursive generator. So recursion already was like you understand the secret is that there is no secret. Generators take a sequence built on an existing sequence, and if the existing sequence happens to be a smaller of the same type, that doesn't make any difference to anything than if it was a 4-tail in range, blah, blah, blah. So nothing makes any difference there. So this one I think is a really good example, like how simple Python makes this. So this same example, it wouldn't be this simple at all if we did it in Java or a similar language. Whoops. There's gotta be a better way to stop the recording, but I don't see where it is, so sorry about this.